So they have these little grants for like 20K where you can apply and then you become an explorer and then become part of their like general community, and then it opens up more grant opportunities actually. But they also have like all these events, and so far the only thing that I've done is like this Zoom session that was like a show and tell of like everyone's projects, but it was super cool where everyone spent like 3 minutes being like, I'm fighting forest fires and I'm like in Zambia studying chameleons, and like I was like the space person, and so yeah, so I think it's mostly like you become part of this like community thing, but it's also comes with money. Yeah, like they opened up a new space branch, so they like want to invest in space more as of like this past year or something. And I didn't even know when I applied.
Yeah.
And, like my program officer was like, "Oh yeah, we're like trying to do more with space stuff."
That's super.
Super supportive, and they like want to help people to like get in with the media and whatever. I still don't really know what that means because I haven't tapped into that yet apparently. But yeah, it's a good group. I feel like I'm usually like trying to look out for that kind of thing, just because it's like fun, novel communities that we don't like normally think
because
about
like there's
joining,
like the obvious things to like apply towards. So.
yeah,
That's cool.
yeah. So yeah.
Go ahead.
Hello, everyone. Thank you for coming to the ITC Colloquium this morning. Today, we'll be hearing from Professor Malena Rice. She is a planetary astrophysicist and assistant professor in the Yale Department of Astronomy. She received her PhD in astronomy from Yale University in 2022, and holds dual BA degrees in physics and astrophysics from UC Berkeley. Her research focuses on the formation dynamics of planetary systems. Professor Rice also holds leadership roles in NASA's ExoPag and Habitable Worlds Observatory initiatives. Today, she will be telling us about insights into orbital architectures of planetary systems. So, everyone, here is Professor Malena Rice.
Great. Thanks everyone for joining. This is actually the second time I've given an ITC colloquium, but the last one was on Zoom, so it's really nice to get to be here in person. My last one was in 2021. I was talking about Planet 9, which is completely different from the stuff that I'll be talking about today. But I'm generally just interested in understanding kind of the underlying physical processes that shape sort of how the solar system fits into a broader context. And so happy to talk about some of the other things that I also do, Planet 9 and otherwise, later on if you're interested. But I'll be focusing on exoplanets for this talk and specifically looking at what we can learn from the orbital architectures of these systems about their past evolution. So I wanted to start by just giving a shout out to my wonderful research group, one member of which is actually here today, coincidentally. So Tiger happens to be in the audience, but I am talking about a lot of work that has been enabled by this fantastic group. I started at Yale 2 years ago, so these are the postdocs and grad students that are actively working in my group. And we also have quite a few undergraduate students, so it's been super fun. This is kind of my favorite part of my job, is getting to work with these people. All right, so if we look at a very, very basic schematic of a planetary system, this is a sort of solar system-like schematic. This is actually not so dissimilar, and maybe is more information that we have than what we have for most of our exoplanet systems, and that we actually know that there are 8 planets there, maybe a 9th, who knows? and we can see that there's our host star at the center. If we sort of flip this around and then consider some of the other elements of this system that we can learn about, in exoplanet systems, there are a couple of additional things in addition to just where those planets are and their masses and their radii that we can also learn. So one that I'm going to be focusing on in this talk is this thing called the spin-orbit angle, or in this case, it's the stellar obliquity, because we know where all the planets are, we know how the angular momentum is distributed within our system. And so we are able to say, okay, this is the angle between the stellar spin axis, our sun's spin axis, and the net orbital angular momentum vector of our system. That's defined as the stellar obliquity. In exoplanet systems, primarily, we are looking at individual planets' orientations relative to the host star, but this is also something we can measure. So this will be the first part of my talk, where I'll be discussing what physical mechanisms can cause these tilts in planetary systems. In the second half, I'll be talking about the fact that many of our systems are not just single planetary systems. Often we will actually have another star that may also have planets within that system. And so I'll spend some time discussing how these stellar companions are influencing the first star and sort of what the interplay is between those, some inroads that we can use moving forward to try to look at these binaries in more detail and understand what we can learn more broadly about planetary systems from them. All right, so I'll start with section 1, which is what physical mechanisms are tilting our planetary systems. So I mentioned the solar system looks sort of like this. There's a 7-ish degree tilt between the net orbital angular momentum vector of all of our planets and our stellar spin axis, our solar spin axis. But if we look at hot Jupiter systems, then they are often on these kind of wacky orbits. Sometimes they are oriented similarly to the solar system, but sometimes they are quite distinct. And so many of these hot Jupiters have been found on very heavily misaligned orbits from their host star's spin, sometimes going sideways or backwards. There are a lot of ways that one can misalign a planetary system. So if you see some misalignment, this first of all is sort of implying that probably most of these mechanisms have not occurred within the solar system, but in extrasolar systems, perhaps one could imagine that you could either tilt your system before the disk disappeared, so that's this primordial set of misalignment mechanisms where there are quite a few ways that you could say you somehow managed to tilt your disk itself, and then you form a planet quiescently within that disk. That is tilted from the formation standpoint. Or after formation, you can say there are a lot of different dynamical mechanisms, some of which require a companion star, or if you have other planets in the system, you can also misalign your planet using one of these post-formation mechanisms. So this is sort of an overview of the range of ways that you might interpret an individual spin-orbit misalignment. And so what we're going to do is look at the population and try to figure out which of these is most likely prevalent, and then beyond that, there's a lot that we can parse as well into which of these mechanisms is actually at play. So for hot Jupiters specifically, which are the ones where we have most of these measurements right now, this is kind of showing the two paradigms and the ways that this fits into hot Jupiter formation. There's been this long-standing argument since the discovery of the first hot Jupiters of whether hot Jupiters are forming quiescently. They form within the disk plane, remain within the disk plane for their entire lives, which would line up with this picture that's on the left. Tilted planets form in tilted disks. You don't need to do anything dramatic to the planet after the fact. Or you could instead form your hot Jupiters through dynamics after the disk has dispersed. So there are a lot of different ways that this could look. If you have overlaps of secular resonances, if you have Kozai-Leidov oscillations and high eccentricity migration, something that leads to a very highly eccentric orbit, then you can tidally inspiral your hot Jupiter. And ultimately what we end up seeing is just this endpoint. So what we're trying to do is interpret what is actually leading us to this endpoint that has been observed in many cases, these misaligned hot Jupiters. There are lots of things that we can learn from these stellar obliquities beyond hot Jupiters, and so some of this is related to hot Jupiter formation specifically, so how do hot versus warm Jupiters form? But there are a lot of other things that you can sort of piece together a broader picture of the evolutionary histories of these systems by trying to understand the global properties of your planetary systems and how they fit together with the obliquity distributions that are observed. So this is actually a slide that I put together a few years ago, and I think we've made some pretty good progress on most of these questions that I will outline over the coming 20 to 30 minutes. So just stepping back, how do we actually get this measurement in the first place? There's a reason that it's pretty limited to hot Jupiters, and that's because in order to actually get these spin orbit orientations, we need to have a transiting exoplanet, and it needs to produce a sufficiently large signal that we can actually see it, which tends to favor hot Jupiters for most of our exoplanet cases. So the way that we can actually make this measurement, and this has been done for over 100 years at this point for binary star systems, but has more recently been extended to hot Jupiters, is if you have a transiting body, so in this case our planet, it will cover up different parts of your spinning stellar disk, different points in its orbit, and if you just pull out a radial velocity observation from it, it will look slightly redshifted or blue shifted because you've taken out a chunk of the bluer side or the redder side of your stellar flux that is being obtained that is causing this line broadening. And so what this ends up looking like, and I show this mostly just to contextualize some data that I'll show later, is if you have a symmetric signal and your planet is spin-orbit aligned, then you get something that's on the left here. So if you see a nice symmetry, that means your planet's going the same way that your host star is spinning. That's more similar to the solar system. And if you end up with a very asymmetric signal, like what's in the middle or the right here, then that would be indicative of a spin-orbit misalignment. And this is just kind of quantifying how big you actually expect that signal to be. Very strong function of transit depth as well as V sin I. So this is easier to do for stars that are spinning faster. So this is just the types of systems that we actually expect to see this for. Okay, so in 2010, there was a result that came out that showed that hot Jupiters around hot stars are more often misaligned than the ones around cool stars. So this is sort of a line that is defining what they call hot versus cool stars within this work. And so just to draw your eye to what's actually being shown in this figure, at the bottom you can sort of think of these as spin orbit aligned. So each of these sort of measurements across the transit from this, each of those turns into a single data point onto this plot, and you can get some lambda value. So the ones that are at the bottom you can think of as spin orbit aligned. The ones that are in the middle are on roughly sideways orbits, and at the top you can think of as retrograde orbits. That's not a perfect mapping because this is a 2D projection of a 3D angle. So it's not necessarily actually perfectly 90 degrees or 180 degrees. You're missing this line of sight angle, but you can sort of see that the ones that are way up here are not aligned, certainly, even if we don't know the exact number for exactly how misaligned they are. So this is what was pointed out by this paper, and the way that this was interpreted was that above the Kraft break, where you have this rotational discontinuity, stars are spinning faster, you have a radiative envelope and a convective core for your stars, tides will not effectively dissipate energy, whereas below the Kraft break, they will. And so just using a very simple kind of equilibrium tides framework, this paper said, okay, well, if you just consider that the systems that have this larger convective envelope in the outer region of their host star are the ones that tend to be aligned, then you can interpret this as those are systems that were realigned, and perhaps all your hot Jupiters started off with this very broad range of spin-orbit orientations. Some of them were damped, and some of them were not. So that was kind of this initial framework that came from this observation from over a decade ago now. And now, 15 years later, this still holds very nicely. So as more and more of these observations have been taken, there are now over 200 of these spin orbit measurements obtained. And we're still seeing that the hot stars, there's a broad range of these misalignments. We're seeing lots of sideways, backwards orbits for their hot Jupiters that are around hot stars, but around cool stars, not so much. So pulling this back to what does this actually mean for hot Jupiter formation, if we go back to this picture and want to figure out which of these channels, this pre-formation or post-formation misalignment is prevalent, we can see in this schematic, you actually need to have a high eccentricity for your orbit at some point, whereas on the left, there's no particular reason that you would ever need to have this more excited orbit. And so one thing that you can look at then is, okay, now that we have a larger sample, is there any reason to believe that there is a relationship between higher eccentricities and these spin orbit misalignments that might indicate something on the right here? So if we look at just all the hot Jupiters that had been obtained as of a few years ago, this was a work that I did in 2022, what we ended up finding is that the hot Jupiters that are on eccentric orbits are often spin orbit misaligned, and specifically this difference at the Kraft break is actually only really prevalent for circular orbits. So what we're showing here is, in purple, is a cumulative sum of lambda, so it's just kind of showing that a linear fit here would mean that below and above the Kraft break, effectively, you get similar spin orbit orientations. So that's the eccentric planets that are in purple. Those are E is greater than or equal to about 0.1, and we tossed anything that looked ambiguous. So anything that was pretty definitively circular orbit, the data looked very clearly that it was on a circular orbit, was the sample in gray. And the ones that are very definitively on a non-circular orbit are in purple, and we kind of tossed everything that was ambiguous between e = 0 and 0.1. So what we're seeing here effectively is that we get this shallower slope below the craft break, and then it goes upwards above the craft break, where that's sort of this thing that I mentioned where the cool stars, you tend to see spin-orbit alignment, and the hot stars, you often see this misalignment. So that manifests as this difference in slope there that we don't see for the eccentric orbits. Another way to visualize this is to take, so this is sort of the same idea, is to take all of your systems and just put them in 4 bins, where you say, we're looking at circular orbits, eccentric orbits, hot stars, cool stars. And overplotted with this is also several mechanisms that have been proposed as kind of initial starting points for high eccentricity migration. And so you can see that actually all these distributions sort of line up pretty nicely with these mechanisms that are, again, where high eccentricity migration is expected to put your obliquity distribution, except for this purple line that is the planets that are on circular orbits around cool stars. So really what this is ultimately showing, just to kind of put this in simple terms, is this is what we have known since 2010. This has been pretty clear and has held up pretty nicely. But if you break it into this sort of eccentric and circular orbit paradigm as well, there's really only a very clear difference in the above and below craft break obliquities for the systems that are on circular orbits. And so what this hints at, I'm not saying that this in itself is telling us that this is the case, but it hints towards this potentially being our paradigm for hot Jupiter formation. There's more that we can do to actually decide more definitively which of these we think is more prevalent, and so there are some other ways that we've also approached this since. Hot Jupiters specifically are really close to your host star, and it's hard to tell, actually, if you see a spin-orbit alignment, if it's primordial or not, because we know that some of them could have probably been realigned by tides. But if you look at warm Jupiters, they're just a bit farther. I define this in A over R star space, so it's on a sufficiently wide orbit, at least 11 stellar radii away from your host star, such that it's less affected by tides. And warm Jupiters kind of also have lots of planetary neighbors. We think they probably couldn't have formed through high E migration. So then if you compare them with your hot Jupiters, then you can try to figure out what is producing the hot Jupiter population that has very few companions, that is often spin-orbit misaligned, versus the warm Jupiters, where until recently we weren't really sure what their obliquity distribution looked like, but we know that they have lots of companions, and this last channel that I was advocating for on the last slide doesn't really work for our warm Jupiters. But really the main motivation is that it's just easier to not have to kind of parse, did tides affect the system, did they not? If you see an aligned warm Jupiter, then it could not have been tidally realigned. So you can say more about what that primordial distribution actually was. So this initiated this survey that I've been working on since my PhD, together with Songhoo Wang, who's an assistant professor at Indiana University, and Shanyu Wang, who's a postdoc at Indiana University. This emerged from me just making like 200 figures and just being really kind of surprised by this one in particular, where I noticed that if you look at hot stars, where your planets are on relatively wide orbits, almost none of them are spin orbit misaligned. And so I mentioned, like, we kind of expect this region to be, like, all of your systems should be towards the bottom of the figure. Here, they should be scattered throughout. But then if you look at wider orbital periods, that didn't really seem to hold very clearly, but there just wasn't a lot of data. So we said, okay, let's fix that. Fortunately, at about the same time was when a lot of test discoveries were starting to be confirmed. And so there were a lot more warm Jupiters that we actually could get these measurements for. And so we have obtained a whole bunch of these Roster-McLaughlin observations over the past couple of years. This is showing our first 10, and I'm delighted to say that I can't fit them all on a slide anymore. So now we have 20 plus that have come from a range of papers that have presented these individual results, but that have also, in many cases, sort of had other interesting results kind of in their own right. And so I'll talk through a couple of them that I think provide especially useful insights for trying to figure out hot versus warm Jupiter formation. So the first of these is that a few years ago, it became pretty clear that in single star systems, if you throw away your binaries, that can undergo a whole slew of other dynamical processes. Just consider the single star systems. We were seeing that all of the warm Jupiters, which again, we define as A over R star greater than about 11, it's sort of an empirical boundary really, they're all aligned. So that's these kind of pinkish points that we see, as well as some of the yellow ones. This is not so true for Saturn, so I'll kind of get back to that point and what's happening with the lower mass planets, we think, but potentially they are easier to scatter, and so it might just be that they are preferentially the ones that get spin-orbit misaligned because of companions within those systems. So just looking at how significant this is from just a very basic drawing from random distributions of your hot Jupiters versus the warm Jupiters, taking different cuts if you're considering the full systems versus also accounting for stellar biases and other things. The significance of this ranged from about 3 to 4 sigma a few years ago. Now, so since then, we've been getting more of these observations, and interestingly, this seems to hold even when you have extremely eccentric orbits for your warm Jupiters. So these are quite eccentric. That would often be indicative of something probably happened after the disk to reach an eccentricity of 0.8. That type of eccentricity is often associated with Kozai-Leidov oscillations or something else, but there is no companion star within these systems. And even those ones tend to be spin-orbit aligned. So we are not seeing any spin-orbit misalignments for any warm Jupiters in single-star systems still, even despite these very high eccentricities for some of them. This also seems to hold even as a function of host star property. So this is just a slew of additional measurements that we got that then kind of add on to this warm Jupiters all falling at the bottom of this figure, whereas hot Jupiters are kind of scattered throughout that full range at the top. And so we found that, again, when you get more of these measurements for the hot stars and you are able to bin by hot and cool stars, we're still seeing the strong alignment for the warm Jupiters. So this is all, to me, really pointing towards the hot Jupiters being distinct. So we're seeing that the warm Jupiters are probably basically never spin-orbit misaligned, which means that their disks are probably aligned for the most part. And then the hot Jupiters are probably some sort of population that is on top of that. A couple other lines that are other reasons that I believe this is, in addition, if you look at the near-resonant planetary systems, which are the ones that we think are closest to pristine, probably have not changed very much from formation. They also don't span a very broad range of misalignment. So the most misaligned one that has been found to date, although error bars, but the one where the mean value is most misaligned to date, we made this measurement a couple years ago, and it's still only something like 30 degrees off. So there's probably some range of misalignment that you can get primordially. Your disks aren't perfectly aligned. Remember, solar system is 7 degrees off. But you're not getting these fully backwards orbits and kind of crazier things that you get for hot Jupiter systems when you're looking at any of these warm Jupiters or near-resonant systems or systems that we think are maybe better tracers of the primordial obliquity distribution. So that, again, points to hot Jupiters then, by contrast, sort of forming from something more like high E migration. I mentioned I'd briefly go back to just more on like the lower mass planets. And this is a recent result where we actually found that if you consider in planet to star mass ratio space, the range of systems that are misaligned or not, we find that the ones that are at the highest planet to star mass ratio are basically much lower in terms of their obliquities than the ones that are kind of at low planet to star mass ratios. And so this is sort of suggesting that there is probably scattering, maybe other companions in the systems that are making it easier to get to these higher obliquities for the systems on the left. For the cool star systems, there's some range where you get tidal realignments that you aren't really seeing for the hot star systems. But then there are also probably some subset that is primordially aligned. So I think this is a nice summary plot of kind of the range of processes that are occurring for many different parameters across this space. And then there are other things that you can learn about. So I know some of the folks I think in this room have also been looking at brown dwarfs and getting these spin orbit measurements there. So that's really a nascent area. You can see since this paper that was 2024, there were only 5 5 or 6 of these measurements that had been made, and there have been a few more since. This is, I would say, too early to interpret exactly whether brown dwarfs are forming kind of similarly to hot Jupiters or in a very different way, because many of these measurements are for systems where it's hard to disentangle whether they were realigned or whether they were primordially aligned. But as more of these transiting brown dwarfs are being discovered, that's also a really cool area that you can start pushing into with these measurements. Okay, so that's obliquities. I want to talk a bit about stellar binaries as well. So I actually got sort of interested in this somewhat through this obliquities survey that we've been doing, because there was one warm Jupiter that we found that looked pretty normal, spin orbit aligned pretty precisely. That's kind of what we expect from everything that I've said so far. But then when we looked into just more properties of the system, we found, okay, there's a stellar companion here. We looked at how it was oriented relative to the rest of the system, and we found that the position vector between the two stars and the relative proper motion vector are perfectly collinear, or almost perfectly collinear, such that the system is also very, very close to edge-on. So it's very precisely spin-orbit aligned, and it's also very precisely edge-on. And we mentioned these are all transiting exoplanet systems, so that means that both our planet orbit is edge-on, our star orbit is edge-on, and our planet is oriented, orbiting the same direction as the host star spin. So everything in this system that we've seen so far is very, very precisely aligned. And around the same time, there was a pair of results that came out from Christian et al. 2022, an undergrad at MIT, working with Andrew Vanderberg, as well as Dupuy et al. 2022, that were both showing that if you just take the set of transiting exoplanets that have a wide stellar companion, and look at the distribution of the orbits of those companions, you find that they're preferentially edge-on. So our binaries like to be sort of edge-on if our transiting exoplanets are found, such that everything is sort of collinear out to these stellar separations of something like 800 AU or so. So this is surprising that you actually get this collinearity out to such wide separations. And also, this sort of fits into this spin orbit orientation, where it seems like we're getting some of these systems that are just, everything is so beautifully, beautifully aligned. So just to show in animation form what this looks like, we're seeing this from the Christian et al. And Dupuy et al. Results. The other system that I mentioned, Qatar 6, we also see spin orbit alignment. And so I just dug into all the systems that we could actually get both of these measurements for, and said, okay, well, there are a lot of ways that you can configure your binary star system, and you can get these angles in all kinds of different combinations. But we want to see if this set of configurations that's on the top is actually really common, versus if we're getting, these are just a couple of other examples of ways that you could orient such a system. And especially if you don't expect your two stars to be talking to each other too much during formation, if they're on pretty wide orbits, then you would get kind of a broad range of spin orbit and orbit-orbit misalignments and alignments. So they shouldn't necessarily go together. So digging into just all the systems that had spin orbit measurements that also had binary companions, and figuring out those configurations, we found in a sample of 40 that 9 of our systems all show this joint spin orbit and orbit-orbit alignment. So these are just beautifully collinear systems where everything is very, very nicely lined up, like maybe strangely lined up. And this is actually more so than you would expect from just a primordial distribution. So if you look at isotropic orbits, you do expect a peak actually towards this kind of edge-on system, because you get a uniform distribution in cosine I that puts you at edge-on more often than not. But we're seeing that this is actually even stronger than you would expect from isotropy, which would be sort of this black distribution. And we also see that this appears to be sort of a function of our host star type. So we see this very clear alignment for the cool stars. So if you have a host star that's kind of solar type or lower, we actually set the distribution here at the Kraft break to compare with the spin orbit distribution. But the cooler stars appear to show this very clear, like everything is very aligned in many of these systems in an overdense way. And then for the hot star systems, we see actually to my eye, and this is a small sample, but this looks sort of like what I would expect from Kozai, where you get this double peak at 40 degrees and 140 degrees. That is kind of a traditional kind of outcome of what you would expect from Kozai-Leidov evolution in these hot star systems. And so this is sort of what we're seeing, and it looks like probably Kozai is playing some role, at least in the misaligned systems. For the aligned systems, what we think is probably happening, so this is just Kozai, for anyone who might not be so familiar with it. You trade eccentricity and inclination back and forth, and so you can get really eccentric, really misaligned systems very naturally through this in hierarchical three-body systems. And for the systems that are nicely aligned, that probably are not undergoing Kozai, what we think is probably happening is your stellar companion is going to cause your first star, when it has a disk, to precess. And so it's going to precess about sort of the normal plane relative to the stellar companion. And as it precesses, it will lose energy through dissipation from viscosity within the disk. It's resisting this torque. And it will get closer and closer to the plane of your binary orbit. And so what that's going to do is preferentially push you towards this orbit-orbit alignment at the very early stages of planet formation. And so this is something that's been theorized for a really long time, but hadn't really been directly shown in observations until pretty recently. So this is a strong function of a bunch of disk properties early on. So if you take pretty optimistic alpha values and pretty optimistically large disks, then this works pretty effectively. I still don't think that we've fully figured out like how well to expect this to work. I mean, Constantine did model this and showed that if you assume somewhat optimistic parameters, then you can definitely realign your systems within 400 AU, within maybe 600 AU. But when you go out to 700 or 800 AU, then you don't really get a very different distribution from cosine I being flat would be isotropy. And so you would expect this to just be flat if it was random, and then if you have this peak towards alignment, then it would be more like one of these distributions. So it is still a bit of a puzzle that this lasts out to such wide orbital separations that has been seen in the population studies. But we do think that this is probably playing an important role because if you also just look at another thing that will determine how effective this mechanism is the mass ratio between your two stars. And so if your secondary star is more aligned than your primary star, so it's being influenced by a higher mass companion, you expect this to actually be more efficient. So the closer your star is, the higher mass it is, the more able to influence its companion it'll be. And we do see some evidence for this when we break into sort of mass ratio bins of where our planets lie. So this seems to be indicating probably this precession is playing some role. Maybe there's some element of some primordial relationship between the orientations of your stars, and I'd say that's still a bit up in the air exactly how much each of those contributes, and whether you expect to see some sort of primordial, not perfect isotropy at such wide separations of 700 or 800 AU. Okay, so both of these we think are probably happening. Last short things that I want to briefly talk about. I've been really excited about binaries as a possible way to compare between two different planetary systems recently. So this was a paper led by an undergraduate who worked in my research group last summer that was saying, okay, well, we see all these edge-on systems where your binaries are edge-on, your planetary systems are edge-on preferentially. So if you just identify all of the systems that are in the local solar neighborhood that are binaries that are edge-on, that should actually be if you kind of flip this paradigm, that should be the ideal systems to look for planets, right? Because then you more often will have transits. You also will have larger radial velocity amplitudes, because if they're edge-on, then you're able to actually see those amplitudes better than you would for just random orientations. So what Joseph did was pull out all of these binaries that are relatively bright for both of our stars. So he set a magnitude cut of G equals 14, and just figured out what is the distribution of separations, which ones are more observable. So especially when your stars are closer than an arcsecond, it'll be difficult to actually observe them separately from the ground. But as you get farther up to the top left, then those are a bit easier to actually follow up. And he showed for, this is just the uncertainty on our inclinations for the binaries, as well as kind of the distribution of stellar types that we have for this sample. So mostly FGK, good planet search stars, as one would generally expect. Then you can figure out which of these are actually just the best candidates to maybe search for more planets in. And there have not been as many planet searches that are specifically looking for the binaries because they tend to be tricky. But this could be a good sample to start with, is what we're advocating for. And this is just quantifying if you assume that the systems are exactly aligned with the stellar binary versus some dispersion in the alignments, kind of how much more likely you are to get transits versus kind of how much larger your radial velocity amplitude is. It's boosted by a factor of, the typical factor is something like 1.6. So if you want to look for especially smaller planets, then it might be a bit easier to do that for the ones that you have some reason to believe are more likely to be edge on. So this is something that I think could be really cool, especially if you could find planets around both of the stars. And that would be amazing to actually compare those stellar systems. And then the last thing that I wanted to very briefly mention is that I've recently been kind of obsessed with this WASP-94 system that is the only system that has 2 hot Jupiters that no one has written a paper on this in like a decade. I don't know how this just got forgotten because it's so amazing. Like, I don't think people even know that this is a thing. So these are 2 different stars. Each of them has a hot Jupiter around them. One of them is transiting, one of them is not. And that's crazy because hot Jupiters are really rare. We only see them around like 1% of stars. And so I just got really, really fascinated by the fact that this ever happened and how often does this ever happen. And I don't think people have really been searching the secondary stars of hot Jupiter hosts, and maybe they should be. But one of the things that I've been working on with Tiger, as well as with an undergrad, Nina, is looking at this kind of wacky idea of if you have Kozai migration and you get high eccentricity migration forming your hot Jupiters, if you consider that there's going to be a planet around each of your stars, you could actually potentially produce double hot Jupiter systems through double Kozai. So if you have sort of mirrored migration through this double Kozai mechanism, and if you assume random orientations of your orbits, then this isn't going to happen terribly often, but in up to about 9% of your binaries where your stars are relatively close, if you assume pretty optimistic eccentricities and parameters that will hopefully be unveiled with Gaia pretty soon, you might actually expect to see quite a few of these double hot Jupiter systems. So again, just going back to the schematic of exactly how Kozai works, we're kind of ignoring the fact that our binary star is not just a point source, it probably also has planets around it. And so considering both of those systems together and how they co-evolve was kind of the goal of this project. And this is a paper that Nina, who's only a third-year undergrad, has submitted and got a great referee report for recently. So keep an eye out for that. All right, I think I've gone a bit over, so I wanted to just leave with my conclusions. On the top 2 of each of these segments are conclusions from part 1 and part 2, but I also wanted to just put out some like open questions, because I think this is a good space to get thoughts from a lot of very well-informed people about kind of what you think might actually be the answers to some of these. So I will leave it, and I will take questions also, but I would love to hear your thoughts on my questions too. Thank you.
Thank you. So I wanted to ask first, so you showed a lot of evidence for misalignment after disk dispersal. Do you think primordial misalignment is also important or contributing? Like, is there any evidence you find compelling there as well?
Yeah, I think it can probably happen. I think it's not the norm, but that isn't to say that you can't misalign your systems especially if you have a companion star, if you have other perturbers in the system that would have produced this primordial misalignment. One other caveat that I should mention is that what we're probing with these hot and warm Jupiters is the very innermost part of the disk. So there have been studies that have found, disk shadowing, where your components of your disk are not necessarily aligned with each other. So if you look in the outer segments of your planetary system, it's not necessarily all of your disks are fully aligned. You can have part of your disk aligned and part of it not aligned. So I would say it's the norm for the inner component of your protoplanetary disk to be aligned at the point that planet formation is occurring. But what's happening in the outer system, less clear from the current observational data, at least. There have been some studies here and there, but it's pretty small sample sizes at this point.
And Morgan?
So one thing that you know well is obviously all of these things are convective, well, as pre-main sequence stars. So it's kind of weird on some level how well the craft break predicts all these differences in the populations, And it kind of tells us that they happen over time rather than right away. Like on some level, if the craft break, if the tidal dissipation was happening all on the pre-main sequence, right, we wouldn't expect these differences to show up at the main sequence properties of the star. They might, depend.
Yeah.
And maybe
Yeah.
I'm missing something, but I guess I was curious then, how big of a range of stellar masses are we probing as we're looking across like these warm to cool stars? And like, is there, because that sort of maps to lifetime differences. And are there cases where you think, these stars are evolving so much faster that they don't have time to, say, align or that sort of thing?
Yeah, are you referring to spin orbit alignment or orbit alignment?
I was
Just so
thinking
can-
more about the spin orbit alignment component and like this
That's the
diagram
figure I'm looking
that
for.
it
be
takes
looking
some
for
amount of
this one.
time to produce those alignments if they're dynamically misaligned and then eventually aligned.
Yeah, it's challenging to parse because the ones that tend to be misaligned are also the younger ones, but that's because they're also high mass stars. And so there's this bias where we observe them at younger ages, but they're also the ones that we expect to be less efficient at tidally realigning.
I see. So I'm thinking about like the total lifetime of that star, but there's also the moment when you observe it is like
Yeah,
how old
yeah,
it is.
yeah.
Okay. Good point.
And something that I didn't mention is also, because you mentioned the pre-main sequence, you could magnetically realign the systems through like coupling with the disk very early on, and that is also more efficient for the cool stars. So that's another part of this to parse is you don't necessarily have to tidally realign after the fact. You could realign earlier on and then just form through that alignment. But then maybe the issue there is if you believe all your hot Jupiters formed that way, then I guess you would have to say none of them are forming through like Kozai or something else if you end up seeing them aligned in the end, unless you believe that they tidally realign later also.
Yeah.
So
That makes sense. And on some level, it's weird because even your hot stars were cool in the past. So, in a sense.
yeah, there have been some cool studies recently looking at post-main sequence stars and spin orbit orientations by Nick Saunders, who is an incoming postdoc in my group, he is looking at stars that used to be above the craft break and that are now below the craft break.
Okay.
And they are mostly aligned, but there are only 3 or 4 of them, so it's a little hard to say, but you can try to put some limits on how long tidal realignment takes, but you don't know how misaligned it was in the first place, so it's difficult to do for just a couple of
Yeah,
planets.
but once you have a population, presumably you can.
Yeah.
Out of the distribution. That's super cool.
Yeah.
So the nearest stars are in Alpha Centauri, and there is a binary that is pretty close of solar-type stars. And what are the constraints about hot planets currently, and is it conceivable that there is something there? It may not be a hot Jupiter, but it could be a hot rocky planet.
Yeah, I think there's been a debate back and forth about whether planets exist in that system. I don't remember what the current status is. I want to say there's a confirmed planet somewhere in that system. That's a short period. I don't think so. I think it's a small planet, like a small rocky type planet. I could search this. I don't know if I should search this right now. Right. Yeah. Yeah, I agree. It's not transiting, but I think it's one of those radial velocity planets that there have been all these proposals of planets that have, I'm sure you know, that have gotten killed and then have come back and have gotten killed. But I think there's one that people, maybe 1 or 2 that in that system that people actually believe now and is confirmed formally on the NASA Exoplanet Archive. But I could look this up, but I don't know if I should do that in the moment. I could do it. I'll do it as we're taking a question.
I don't want to interrupt you looking it up, but
This feels like I'm back in class teaching. Just Googling stuff on the spot.
We are always students.
Yeah, we are always students. That's why we're here. I'm going to blame the Wi-Fi here for this.
Yeah, but our Wi-Fi's not working. Well, let me ask a question while you wait. So I was curious if you could sort of turn this around, although I'm distracted now by Morgan's point about,
Or candidates. Oh, there's one confirmed. And that's
No, that's Proxima, right?
yeah, it's
Proxima.
Proxima.
Yeah, Alpha Cent
A and
is.
B. The question is, do A and B that
Yeah. This was a false positive, so nothing.
There is nothing reported.
Yeah.
Okay. So I'm wondering if you could sort of turn this around, because you sort of mentioned this magnetic interaction in the pre-main sequence phase. And I'm kind of, in some sense, I find it kind of surprising, unless there's post-disk evolution, that you do have spin-orbit alignment at all, because in the cases where we're actually able to know anything about the star and the disk alignment, they're always misaligned, presumably by magnetic interactions. There's not that many cases where you can do that. So I wonder if you could just say that if you could sort of turn this around and learn about the prevalence of the stellar magnetic field coupling to the disk magnetic field in the inner disk, and if anyone's thinking about that, because it's sort of an interesting time, but I'm now distracted by what Morgan said about pre-main sequence evolution, because I do think that kind of complicates things.
Yeah.
But certainly you
It was a
don't.
question Josh Gwynn asked me.
Okay.
So I shouldn't take too much credit, but it is puzzling, right? Because all
Yeah. Yeah, so it's not,
Yeah.
not a really well-defined question, but indeed, in the cases where you can actually measure, basically from spot periods, how the star is oriented, and then you can actually see, in some sense, from the disk is oriented, they're never that aligned, at least in the inner disk. And then there are these weird cases where you see basically face-on disks, and then you have these dipper scenarios where the inner disk and the outer disk are maybe actually totally misaligned, which is maybe acceptable in some sense.
Yeah, you're saying from spot crossings, there are a lot of misalignments found? And
Yeah, I'm
that's-
thinking like, something like a tau or something where they actually have, periodic measurements that you can actually just say if the star is spinning like this, and then the
Yeah.
disk is totally misaligned. But you're sort of picking those out in a probably biased way. So just because you would never notice it unless it was extreme. But I'm wondering if you
Yeah.
could take the planet results and basically say a lot of these are actually aligned, and then learn something about magnetic interactions in the inner disk.
So the systems with the spot crossings that you're referring to, are you talking about young systems or
Yes.
main sequence? Okay.
Where they
Yeah.
still have a disk.
'Cause I know there have been main sequence spot crossing studies that seem to align pretty well with this craft break
Yeah.
idea, and so
I'm talking
it's
a
interesting that
million years
before.
old.
Yeah. Yeah. And when you say misaligned, where do you draw that line?
I think it's hard
This
to
is another-
detect unless it's sort of, more than 45 degrees.
Yeah.
Like strongly misaligned.
Huh, okay, so that would suggest that maybe it really is tides after the fact, right? Am I
Well,
interpreting that right?
I think there's a pretty big bias on the observing these misaligned systems. You're much more likely to see them. So I was hoping that you could turn it around and tell us how likely they might actually be based on the alignment that you see in the planet systems.
well, like if you take the current alignments and
Yeah,
just
and say they
that was the case in the
preserved,
past.
yeah, but
Yeah,
then you screwed
okay.
me up, but yeah.
Yeah. Yeah, I know there have been some studies looking at both how debris disks and protoplanetary disks aren't aligned as well, and I
Yes.
haven't seen anything that made it very clearly obvious that there were very strong misalignments in many cases. So I wonder if that's kind of the exception but not the rule. But like as you mentioned, it could be these biases. But I would love to know what paper you're referring to, because I would love to read that paper. I think that would be useful to add to this picture more broadly. Yeah.
In terms of the bulk properties of the planets, I wonder if you've seen any correlation between misalignment and inflation. Like, are the hot Jupiters that are misaligned more inflated?
Yes, but this is yet another degeneracy where we know that hot Jupiters that are getting a lot of irradiation are inflated, so they tend to be the ones around hot stars. And so it's unclear whether the puffiness is related to this tidal evolution that's helping to puff them up, or if it's just that they are getting blasted by their host stars preferentially. So it may or may not be related to the orbital evolution. I have looked into, I mean, the samples are kind of small, but it does look like a lot of the systems that are heavily misaligned are spin-orbit misaligned, and so WASP 107b is a good example of this, where this was actually this beautiful study that showed that you can't actually inflate it to the point that it has been observed without invoking some sort of tidal factor that it has a very small eccentricity, but it has a non-zero eccentricity, and so you can invoke this extra tidal heating that I think is the reason you see methane or something. I don't really do atmospheres, but so it allows you to explain some of the chemistry in that system as well. So that's a really nice kind of weaving together all of these ideas, and I would like to see more of that, but it's hard to disentangle for the hot Jupiters because of the fact that all of these trends sort of could independently point towards, puffy hot Jupiters around, or puffy hot Jupiters tend to be misaligned, but that's not necessarily because of their evolution. It could just be because of their current orbit.
Any additional questions? I had one last one just because I was curious. You showed some extremely eccentric warm Jupiters. How did that happen? How do you think that came about?
Yeah, that's one of my questions that I pitched to everyone. Yeah, that's why are there so many highly eccentric orbital-aligned warm Jupiters? Yeah, I have been told by Cristobal Petrovich that this falls out of his planet-planet scattering simulations from 2015 beautifully, but he hasn't published it.
But why?
So maybe that's something that it's not obvious to me. It's probably not Kozai, and these are single star systems, so it must be something that's intrinsic to that system in itself, and so it probably does need to be scattering somehow all within the plane, which, I mean, there's some, it's not perfectly aligned, it's up to 20 or 30 degrees, so maybe you don't get huge inclinations from that scattering, but I would like to know what that tells you about the underlying distribution of what other planets would have had to be in those systems. Because presumably, you couldn't have just the warm Jupiter itself. Maybe that means in those systems you get a bunch of giant planets that scatter, and then you need to do that to produce these really high eccentricities. But I would say that is a totally unanswered question at this point, and I think they're really strange and fascinating.
Cool. Well, in that case, thanks everyone for coming.
Thank you. Yeah. Prep talk number 2. One down, one to go. Yeah, thank you.
Oh yeah, no, this is a great talk.
Thank you. Thanks. Yeah.
I don't know if you looked at any of the yeah, but I didn't.
I know that there are some that, like, you can see it very early on, like HK Tau, I think is one, where they're like very clearly
Yeah,
misaligned.
there are I think 4 or 5.
So this project actually started because I was trying to figure out how to collaborate with my friend who does discs, Consti,
Oh.
and we were like, what if we wrote an ALMA proposal? And then we like never did because we didn't know how to use ALMA. but I want to see some sort of like actual systematic study, and it's so easy. Like you just need continuums. You don't need molecules or anything.
Is this yours?
No, it's not.
But I'll bring it up. I was
Yeah, no, don't worry. It's all good.
good job.
That was really lovely. Thank you.
Yeah, thank you for the great question.
I think probably we should leave for a little bit and then come back.
Yeah. My stuff is really here.
It's being like leave and then basically just go back.
Yeah,
by.
they seem busy.
Thank you. Yeah.
They sort of reconfigure the room.
Yeah. Yeah. I've seen you've been doing some cool planet engulfment related.
I don't. Maybe do you want to walk down the hall and we can come back in 15 minutes? If you don't mind.
Then we'll try and to get that shelf.
Oh, yeah, definitely. Good call.
We're gonna throw a couple over here to fill the gap. What do you think, Bob? We're looking all right, huh? Hey, where's your clock?
So you'll do one sparkling, one water, and then observational. Okay. Thank you.
You know, you gotta know what time it is out here on the streets.